Hello friends, now in this lecture we will start new chapter, that is real numbers. Real numbers. So before we start the content of this chapter, we'll quickly see the classification of the number that we already saw in our previous classes. So here I will start with classification of numbers. Okay, in this very first is natural number. Okay, and I hope you are well aware about what natural numbers are. Natural number generally denoted by capital N, and they can start from 1, 2 and goes up to infinity. Counting numbers are the natural numbers. Okay, I am not going to give the definitions over here, just will quickly revise the numbers. Then after that we get whole numbers. Whole numbers denoted by capital W. Now if we include 0 in the collection of natural numbers, we will get whole numbers. That means it gets start from 0 and it will go up to infinity. Okay, then after the whole numbers, next we will see although we have even numbers, odd numbers. Okay, so let us see even numbers as well, it doesn't matter. Even numbers. Even numbers generally denoted by capital E. So numbers which are divisible by 2 are called even numbers, and 0 is also an even number, so we write the even numbers in that way. Okay, then odd numbers. Odd numbers generally denoted by capital O. Numbers which are not divisible by, which are, see, even number we can say whole numbers which are divisible by 2 are even numbers, and odd numbers those whole numbers which are not divisible by 2. So that gets start from 1, 3, 5, 7 and up to infinity. Then we'll get positive number, negative numbers, but here next we will see integers. Integers denoted by I or Z. Integers. So integers we can say a collection of negative numbers, 0 and natural numbers, or we can say collection of negative numbers and whole numbers. So it gets start from minus infinity. Okay, then here I do write minus 3, minus 2, minus 1, 0, 1, 2, 3 up to infinity. So these are the integers. After integers we can say there is one more type of number, that is prime numbers. Prime numbers, so numbers those are divisible by the number itself and the 1 only. That means we can say there are numbers, there are only 2 factors. Those numbers who have exactly 2 factors. So numbers divisible by the number itself and the 1 are called the prime numbers. So collection we can say get start from 2, then 3, then 5, 7, then 11 and so on. Okay, these are the prime numbers. 2 is the only even prime number. 2 is the only even prime number. Okay, other than 2, all prime numbers are definitely odd numbers. But all odd numbers are not prime numbers, isn't it? In the list of odd number we have 9, which is not a prime number because it has more than 2 factors. Then after prime numbers, next we'll come to the rational numbers. Rational numbers. So rational numbers generally denoted by capital Q or Q. Okay, here there isn't any special symbol for prime numbers, but we are writing P. Okay, so rational numbers Q. So numbers that are possible to write in the form of p upon q with two conditions, that is q should not be equal to 0 and p and q must be co-prime. Co-prime means two numbers which do not have any common factor. Okay, and p and q are co-prime and p and q are co-prime. Okay, so those are called the rational numbers. Denominator should not be equal to 0 and numerator and denominator should not have any common factor, that is called co-prime. So although this is the we can say revision of the previous year's classes, but still note down because we may need these in this chapter. Okay, after rational number, next is we'll see co-prime number because we discussed over here, so you should understand what co-prime numbers are. Co-prime numbers. Okay, numbers, a pair of numbers that does not have any common factor. Co-prime number. For example, if I write 2 and 3, it's a co-prime number because they do not have any common factor. Okay, then 4 and 5, again they do not have any common factor, so they are co-prime numbers. Okay, now one thing more, see here you can see this is consecutive number, these are again consecutive numbers. So any pair of consecutive number always represents a pair of co-prime number. Now 4 and 9, they are also form a pair of co-prime number because they do not have any common factor other than 1. Okay, so 4 and 9, factors of 4 are 2 multiplied by 2, factors of 9 are 3 multiplied by 3. So they do not have any common factor. So still, see, although 4 and 9 are not prime, still they form a pair of co-prime. So this co-prime has no relation with actually this prime. Do not get confused. Okay. 13 and 11. This is again a pair of co-prime numbers. Here both numbers are prime, still they are prime. Here both numbers are not prime, still they are prime. So to check whether the given pair of number is co-prime or not, simply you have to check they should not have any common factor other than 1. Okay, this is okay. Then after this co-prime, next we can say composite number. Composite numbers. So composite number we can say almost opposite of prime. Prime number says number should not have any common factor other than 1. Okay, or we can say, sorry, prime number says that a number if the number is divisible by 1 and the itself, or we can say a number who has exactly 2 factors. A number who has exactly 2 factors is a prime number. And composite number, if a number has more than two factors. Okay, number having more than two factors are called composite number. For example, 4, it has more than two factors, isn't it? This 1, 2 and 3, so it has more than two prime factors, 4, then 6, then 8. Okay, we can also say numbers those are not prime are called composite numbers. Okay, so these are the composite numbers. So 9, then 10, 12. Okay, these are the composite numbers. Now next is irrational number. Finally we'll come to the irrational number and then rational number, sorry, real number. Irrational numbers. See, rational numbers, which it is, if it is possible to write in the form of p upon q, then it is a rational number. Okay, if you want to add some examples in this, you can write 4 upon 5 minus 3, 0, 1.2, 6.3 bar. Okay, these all are the rational numbers. P upon q, this is again p upon q, 0 upon 1, denominator is not equal to 0. So these all are the rational numbers. So what are irrational numbers? Which cannot be written in the form of p upon q. Those are called the irrational numbers. One thing more, see here with the help of these examples we can say rational numbers have either terminating decimal or non-terminating repeating decimal. In case of irrational numbers, you will find number those have non-terminating, non-repeating decimal. For example, see, if you find the value of root 2, it will never get ends, neither it will repeat itself. So this is an irrational number. Root 2 is an irrational number. In short, we can say any square root of any prime number, square root of any prime number is always an irrational number. Then write 100, 1 3 times 0 and so on. It is also an irrational number because its decimal expansion is neither repeating nor terminating. This dot shows it will go and go so on. It also shows that after 1 000 next will be 1 4 times 0, then 1 5 times 0 and so on. That means it is not being terminate as well as not being repeated, so it is an irrational number. So note down this and then we will see the what real numbers are. Okay, so now let us see the real numbers, what real numbers are. Okay, finally it is real numbers. See, we can say all the numbers from very first to up to 10. That means from natural number to irrational numbers. All are real numbers. So we can say real numbers, the collection of rational and irrational. Rational numbers plus irrational numbers. This is called the real number. In short, if we talk about example, see, it might be a natural number, so 2, it might be a whole number, it might be a negative number, it might be a positive number. Okay, then 4 upon 3, 1 upon 7, okay, root 2, 1.2 bar, 3.6. Okay, these all are the 1.101001000 and so on. All these are the examples of real numbers. All are real numbers. Okay, so I hope this is clear to you. Note it down. Okay, real numbers are generally denoted by capital R. Okay, real numbers are generally denoted by capital R. Okay, now we'll come to the some basic terminology that we have to use in this chapter. So before I come to that terminology, let us consider one example. Suppose we have a number 36, and if I divide this number 36 by, for example, 4, so to I had to read the table of 4 9 times to get this 36, and here remainder will be 0. Okay, this is very obvious thing that you already know. Now what we have to see, this 36 is called actually dividend. Now, you already know this, but in this chapter we have to use this terminology. That's why I am discussing this over here. Dividend. This 4 is called the divisor, and this 9 is called the quotient, and this whatever left is called the remainder, isn't it? These are the terms. Now over here I can say, see, suppose if I say this 36 is equal to B, if I consider this as B, this as A, so and this as C, so I can say if a non-zero integer, if I generalize this concept, I can say if a non-zero integer B is said to divide by an integer A if there exists one more integer C such that AC equal to B, isn't it? Over here, because 4 into 9 4 multiplied by 9 gives you 36, so definitely I can say A divides B, isn't it? Now for example, at the place of 4, if I take 8, and now if I divide this 36 by 8, definitely I won't get any integer such that product of these two gives me this. So this concept can be framed in this way. So here I am giving you one statement that you have to note down. A non-zero integer B, a non-zero integer A is said to divide an integer B if there exists integer C integer c such that integer c such that b is equal to ac. Okay, we'll say that integer a divides b if there exists an integer c such that ac is equal to b or b equal to ac. Here I am able to say that 4 divides 36 because I have another integer 9 such that a multiplied by or 4 multiplied by 9 is equal to 36. In this case I say that 8 does not divide 36 because I do not have any integer c such that 8 multiplied by that is equal to 36, isn't it? 8 multiplied by any integer, there isn't any integer c such that 8 multiplied by that equal to 36. So I will say 8 does not divide 36. So here now after this here you have to continue. After noting down this, you have to write here this b is called dividend. Okay, a is called divisor and c is called quotient. Okay, so I hope this is clear to you. See, this is just is a revision. We already know this thing, but over there in this chapter we frequently use these terms, that is divisor, quotient, dividend. Okay, that's why you can say it's like a revisiting this algorithm. So note it down, then I will give one more point related to this and then we'll proceed in this chapter. Okay, now again I will give you one more point related to this. See, here a divides b, isn't it? 4 divides 36. So in symbolically, when I say a divides b, I do write in this way. Okay, a divides b symbolically written as this and read as a divides b. Okay, so next point that you have to write over here, if a non-zero integer a divides an integer b and integer b, then we write then symbolically it is written as then symbolically it is written as a divides b and read as a divides b. Okay, when a divides b, symbolically we'll write a divides b and this is read as a divides b. Okay, now if A divides B, then see, for a while if I say 4 divides 36, isn't it? Definitely 4 divides 36. So when I say 4 divides 36, can I say 4 is a factor of 36? Isn't it? 4 is a factor of 36. Or I can say 36 is divisible by 4, or I can say 4 is a factor of 36. These three things we can conclude. If A divides B, then A is a factor of B, isn't it? If A divides B, then A is a factor of B. Simply you can say, as 4 divides 36, 4 is a factor of 36. Okay. Or 36 is a multiple of 4. That means, or B is a multiple of A. Isn't it? Here 4 divides 36. So definitely I can say 36 is a multiple of 4. Okay, also I can say 36 is divisible by 4, or isn't it? 36 is divisible by 4, or B is divisible by A. Okay, so when I have this A divides B, I have these three information. Actually I should not say three information because all are same, but we can frame this information in three different ways. First, A is a factor of B, then B is a multiple of A, or B is divisible by A. Okay, so I hope this is clear to you. So note down these 3 points, then we'll proceed in the chapter. Okay, now we'll see the one of the main concept, very important concept of this chapter, that is Euclid's division lemma, or generally known as division algorithm. So next is Euclid's division lemma. Euclid's division lemma. Now what does this word mean? Definitely I will tell you. Euclid division lemma, or I can say division algorithm, or division algorithm. Now what does algorithm means? What does lemma means? Definitely we'll see these two terms as well, but first let me explain you what this Euclid division lemma and Euclid division algorithm is. So here we can go in this way, that given positive integer, see it should be in the exactly same words. So given positive integers, given positive integers, given positive integers a and b, there exists unique integers, there exist unique integers q and r, there exist unique integers q and r satisfying b is equal to, sorry, satisfying a is equal to bq plus r, where r is greater than equal to 0, less than b. This is the Euclid's division lemma or Euclid's division algorithm. Given positive integers a and b, there exist, okay, given positive integers a and b, there exist unique integers q and r satisfying a equal to bq plus r. Okay, so there are four integers a, b, q and r which will exactly fits over here, as well as the remainder. Here r is the remainder, that will be either equal to 0 or greater than 0. That means remainder cannot be negative, first thing. Also the remainder will be less than the divisor. If I compare this with the division algorithm, see this as known as dividend, we already saw dividend, isn't it? B was divisor, isn't it? Q was quotient and R is remainder. So this value of B, that is value of divisor, will be, sorry, value of remainder will be either greater than equal to 0 or less than B. Okay, so I hope this is clear to you. This you have to mug up in a very well manner, because it is quite possible that this exactly this thing can be asked in 1 mark question. Okay, simply they will ask you write division, Euclid's division lemma, or write division algorithm. Then in that case you have to write this in exactly same manner. Okay, now as I told you, we'll see what algorithm is and what lemma is. So here I do write what algorithm is. See, algorithm we can say is set of steps. If you follow those set of steps, we'll get a solution, or we can say rules or method that we have to follow to get the solution or get the answer. But exactly it is written as an algorithm is a series of well-defined steps. Okay, an algorithm is a series of well-defined steps, Okay, an algorithm is a series of well-defined steps which gives a procedure for, which gives a procedure of solving a problem, which gives a procedure of solving a type of problem. Algorithm is a set of rules. As I told you, we have to follow this and this and this and this, then we'll get that. That is, we can say, an algorithm. Okay, now next is lemma. And a lemma is, we can say it is almost near to that axiom that we studied, that you studied in your previous year classes. Okay, lemma means a thing which need not to be proven, but it helps to prove other things. That is lemma. Okay, so a lemma is a proven statement. Okay, a lemma is a proven statement, already it is proved. A lemma is a proven statement used for proving for proving other statements, used for proving other statements. Okay, so lemma is almost near to axiom, which does not require proof, or we can say they are considered as a universal truth, but we can use them to prove other statements. So I hope you got what lemma is and what this algorithm is. Okay, this algorithm and this is lemma. So remember all these three things. As I told you, they can ask you this for 1 mark. Okay, so please note it down. Okay, after this we'll see one more concept of this chapter, that is fundamental theorem of arithmetic. Okay, fundamental theorem of arithmetic. Now what fundamental theorem of arithmetic is, what it want to say, we'll see, but before that let me explain you. See, suppose I need to find the factors of 72. Okay, let us find the factors of 72. Definitely we'll start with 2, the smallest prime, as it is divisible by that, so definitely we'll start with this. So here I'll get 36, then again if I divide by 2 I will get 18, and again if I divide it by 2 I will get 9. Now it is not divisible by 9, so 3, then 3, and then 1. So I can write this 72 is equal to 2 multiplied by 2 multiplied by 2 multiplied by 3. Okay, now suppose again I have to factorize this 72. Okay, again I am starting factorizing it by 72. Now instead of starting with 2, if some student or someone starts dividing it by 3, let's see what we'll get. Okay, now again if I divide it by 3, then here I will get 4, then again if I divide I will get 2, then again if I divide I will get 1. So here I can say 72 is equal to 3 multiplied by 3 multiplied by 2 multiplied by 2 multiplied by 2. Now if you observe these factors, these primes or these prime factors, they are same, just the order is changed, isn't it? Here we have 2 times 3 and 3 times 2. Here again we have the same thing. Let us say another student, and he started dividing it by, for a while, 2. Okay, so then after 2, then he started dividing it by 3. Now again he started divided by 2, then by 3, and then again by 2. Okay, now again if you see its factors, what you will get, 2 multiplied by 3, 2 multiplied by 3 multiplied by 2. But again if you observe, there are 3 times 2 and 2 times 3, isn't it? So this fundamental theorem of arithmetic want to say that if you find the factors of any composite number, their factors will be unique apart from their order. Might be order may get changed, but definitely factors are going to be same. Okay, let us see the same thing with another example. Okay, suppose now this time I take an example 1500. Suppose I find the factors of this. Okay, I started from 2, so here I will get 750. Then again if I divide it by 2, I will get 375. Now if I divide it by 3, I will get 125. Now if I divide by 5, I will get 25. Again if I divide by 5, I will get 5. Again if I divide by 5, I will get 1. So here I can say factors are 2 multiplied by 2 multiplied by 3 multiplied by 5 multiplied by 5 multiplied by 5. Now suppose another student finds the factors or find the prime factors by a different route. Definitely I will say different route. Okay, just he followed the different route. Instead of starting with 2, suppose he started with 3. Now instead of definitely it is not divisible by 2. Now instead of dividing it by 2, suppose he started over here from with the 5. So here I will get 100. Then again let it be 2. So here I will get 50. Then again let it be 5. So here I will get 25. Sorry, 10. Then by 2, so 5. Then by 5, so 1. So again if I write these factors, what I will get? 3 multiplied by 5 multiplied by 2 multiplied by 5 multiplied by 2 multiplied by 5. 3 5 2 5 2 5 3 5 2 5 2 5. Okay, now let us see one more route. Instead of starting with, definitely either we have instead of starting with 2 and 3, suppose this student started finding factors by 5. So here I will get 300. Now next suppose he took 3. So here I do get 100. Now suppose then he took 5 again. So or let it be okay 5. Okay, now again suppose 5. Okay, now again if I write these, so 5 3 5 5 2 2. Okay, so these factors in first look that they are different, but if I make their order same, that means first I write the smallest prime number, then a little bit greater prime number. That means if I write all the primes or all the prime factors in increasing order, let us see what I will get. Here it is already in that way. Here it will be 2 into 2, then 3, then 5 into 5 into 5. Here again 2 into 2, then 3 into 5 into 5 into 5. That means every time we are getting 2 times 2, then 1 time 3, and then 3 times 5. Isn't it? 3 times 5. So this is the fundamental theorem of arithmetic. That means when we find the prime factors of a composite number, definitely the primes will be same or unique apart from their order. Okay, so now we'll state that fundamental theorem of arithmetic. Every composite number, okay, fundamental theorem of arithmetic. This says every composite number can be expressed or factorized, can be expressed or factorized. Okay, every composite number can be expressed or factorized as a product of primes, as a product of primes, as a product of primes, and this factorization is unique, and this factorization is unique. This factorization is unique apart from the order of the primes in which they occur. Apart from the order in which apart from the order in which primes occur. Okay, apart from the order in which prime factors occurs. Okay, this fact is called or known as fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Okay, so please note it down. After this, now we'll see some applications of Euclid's division lemma or division algorithm. Okay, and in this very first one is, and very important as well, is how to find the HCF of two numbers using division algorithm. So here I am writing the very first question. Use Euclid's algorithm So note it down up to this point. Here to write 1. Okay, so now after this again I do write as remainder 124 is not equal to 0. So on applying Euclid's algorithm to divisor 148 and remainder 124 we get. Okay, so here I will show what we'll get. I hope you are getting this. This is a little bit long method, but you have to write all these steps every time. So 148 is equal to 124 into 1 plus, this time I can say this should be 24. 124 plus 24 is 58. But still I will show that thing. That means how I got this, that I will show over here, because when I divided 148 by 124, here quotient was 1, here I got 124, and on subtracting here I got 4 and here I got 2. Okay, now here you can see still the remainder is not equal to 0. That means again I will apply that method. So as remainder 24 is not equal to 0, so on applying Euclid's algorithm to, now this time divisor is this 124 and remainder is 24, we get. What we'll get? Let us see. We'll get over here 124 is equal to 24 multiplied by, okay, so here I will show that thing, that how I will get this. So here I have to divide 124 by 24. Okay, so 24 I think 5s are or 4s are, 24 5s are 120. So here it goes 5s are. So here I do get 120 and the difference will be 4. Okay, so 24 multiplied with 5 and 4. Still the remainder is not 0. That means you have to apply this method once again, this algorithm once again on divisor 24 and remainder 4. Now definitely you can see 24 is equal to 4 into 6 plus 0. That means in next step definitely remainder will be 0. So note down up to this and then I will give you the remaining steps of this solution. Okay, so now I will continue with the same. As remainder 4 is not equal to 0, so on applying algorithm to divisor 24 and remainder 4 we get. Let us see what we will get. Now this time definitely we are going to get remainder as 0 as I discussed right now. So 24 is equal to 4 multiplied by 6 plus 0. Okay, so here I will show that thing, that when I divide 24 by 4, I will get remainder as 0. 4 6 are 24, so remainder is 0. Okay, now as remainder is 0. Now how to get the HCF? Now the conclusion part. When remainder is 0, at that step the divisor is the HCF. Okay, here divisor is 4, so 4 is the HCF. Or we can say in the second last step remainder is 0. Okay, this process ends over here, so definitely this is the last step, so this is the second last step. In the second last step remainder is the HCF, or in the last step divisor is the HCF. So now I will conclude that thing over here. At this stage, as remainder is 0, now I do write remainder at this stage is 0. So divisor at this stage or remainder at previous stage, that is 4, is the HCF of 4052 and 12576. I hope this is clear to you. So every time you have to write the equation as A equal to BQ plus R, where A is the greater, B is the smaller number among the numbers selected. You have to find Q and R by this method, and you have to follow that method. You have to apply this algorithm until you will get remainder as 0. And when you get remainder 0, at that stage whatever is the divisor will be the HCF, or in the second last step whatever is the remainder is the HCF of the given number. So I hope this is clear to you. So note down these two last steps. Okay, now take note down your homework for this lecture. Okay, so example 1 that I discussed over here, that the same, and exercise 1 it's question number 1, all three parts. However, we'll discuss this type of sum in our next lecture as well, but you should have one try. Okay, so this is your homework for this lecture. Okay, so that is all about this lecture. Now we'll meet in next lecture. Till then, bye. Thank you.